I started recording a little bit late, but I promise we'll do another example for anybody who's watching this recording and depending on it. Oops. All right. Why aren't we done here? Huh? Okay, it needs to be bracketed. This is an ion. It has one more electron than proton. So because it's an ion, it has to get a bracket. But we're still not done. I want you to build this right now. Go ahead. Okay, so you've got a nitrate ion here. Now the first thing I want to ask you is, go ahead and stick the double bond down. Hold it up like this. So double bond is down. How do you know the double bond is on that oxygen? You don't. How do you know it's not on this oxygen? I flip it so that the double bond is up at an angle. How do you know it's not on this oxygen? She flips it again. You don't. And as a matter of fact, we said what we know now, we used to think that the electrons like zipped around and did different things. What we know is they're all sort of like a third double bonded, which is weird. The way we show that is with resonance. Anytime you've got something that could exist in more than one location, you have to show it in all the possible locations. I'm going to set those aside. So we know that that double bond could be any one of three places, which means we have to show a double-headed arrow that looks like a G. It's not. I am going to go back and do my move this whole thing over a little bit. Okay, aside from the fact that it's messy, that's what tells us that, hey, there are different ways for this thing to exist. There are different ways for this thing to exist. But what do we call it in terms of ABE code? So wait, okay, stop. Stop, Moser, stop. Does that clarify anything about the concept of resonance, or is that just exactly what I've said before and it doesn't help? It does help? Okay. Okay. That's why we do resonance, because we don't know where that one thing that could exist in multiple places is. Not everything can exist in more than one place. But double bonds in a case like this could be on any one of those oxygens. Okay. ABE codes. That's something people mentioned. So remember that A equals your central atom. B is the number of things attached to the central atom. Messy, messy handwriting. Worst handwriting ever. And E is unshared pairs on the central atom. Okay. One thing I saw was people who were writing down the total number of unshared pairs, or the total number of unshared electrons. So this would be like ABE8, AB16. No! I'm going to shrink all the gooch math here. So every compound has a central atom. So every compound gets an A. We don't need to put a subscript 1 or anything there because there's only ever one. Not how many bonds, but how many things. How many things are taking up space around the central atom? fingers? 3. So this is A, B3. Are there any unshared pairs on the central atom? No. There are no unshared pairs on the central atom. If there are no unshared pairs on the central atom, we don't even put an E. Are there unshared pairs in this compound? Yeah, heck yeah, but not on the central atom. And the ones on those outer atoms, remember we said they don't really change the shape. We don't care much about them. I mean, we care about them in terms of the fact that we have to show them, but they don't change the shape. And the ABE code is all about shape. Okay? So this is just an AB3. And you're done. Look at the thing that you have in front of you. And I'm going to shrink this and put this up here. What shape does that look like? I'm going to draw it right on top of it. Sure looks like a triangle to me. And I had a few people who came up with trigonal but weren't sure what came next. So what is a plane? Not the airplanes. In geometry, think geometry. It's a flat surface. What we want to know is, does this molecule, well, does this ion, does this structure all exist in one plane, or does it form a little pyramid? So if we look at this picture, and it's the best I can do, sorry. You can see that these are all in one plane. It's sort of three-dimensional. But they're all on the same plane. None of them are pushed down. It's not forming a pyramid. So what kind of geometry would that be? Trigonal, planar. So we're going to do ammonia. You can dismantle your little nitrate ion. Where did I set my little nitrate ion? So I don't know if this is a Gooch conformer or non-conformer. Nothing terribly electronegative in here. It's probably a conformer. I do actually know, but I'm not. I'm going into it as though I don't. So I'm going to start off by trying the Gooch math and seeing if it works. So I know that in terms of valence, what this comes in with, nitrogen has how many? Nitrogen has 5. You're getting ahead of yourself there, ma'am. Hydrogen has 1. So we have 8 valence electrons. That's how many valence electrons it has. Okay. How many would this need if it was going to satisfy all of the atoms that are there? Nitrogen wants 8. How many does hydrogen want? 2 times 3, so we get 6 and 8. We get 14 octet. We could call it 14 satisfaction electrons. I don't know. You can make up a new term for it. Now I'm hearing Mick Jagger. No? Can't get no da-da-da satisfaction. No? Okay. Oh well, I tried. So if everything here was happy, if everything was totally satisfied, totally fulfilled, they have 14 electrons. How many would they have to share? How many bonds should we be looking for? We should be looking for 3 bonds because 14 satisfied minus 8 that they actually have, octet satisfaction, that doesn't make any sense. 6 are going to have to be shared. Divided by 2 equals 3 bonds. This helping? No?
Yeah, I didn't really have a problem.
Okay. Can we put a nitrogen together with, well, okay, first I guess we should ask how many unshareds are there? There are 2 unshareds because it has 8 it's sharing 6. That means 2 are unshared. Okay. I'm going to have you do a brave thing. Okay, can I hook this thing together with 3 bonds? Well, what goes in the middle? The most electronegative, or carbon, or gee, I have 3 of one thing and 1 of the other. How about that? Can I do that? Yeah. Is there a place for 2 unshared pairs? Or for 2 unshared electrons? Yeah, absolutely. Boop, boop. And let's check to see if everyone's satisfied here. How many does nitrogen want? 8. 2, 4, 6, 8. Nitrogen's happy. How many does hydrogen want? 2. 2, 2, 2. I saw people who put unshared pairs on hydrogen. That can never happen. Hydrogen cannot handle more than 2 electrons. You will never, ever, ever see unshared electrons on hydrogen. Ever. 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 When will you see unshared electrons on hydrogen? You won't! Doesn't happen. Okay, so let's go back and check all our numbers, and we'll check these off as we go. Are we showing, well, let's see. Are we showing 3 bonds? 1, 2, 3. Yes. Are we showing 2 unshared electrons? Yes. Are we showing a total of 8 valence electrons? 2, 4, 6, 8. Yes. Does this conform to the Gooch math? Yeah. It does. Is there any place else that those unshared electrons could appear? Is there any double bond that could appear in multiple places? Anything like that? No. There's no resonance. This is the only possible way this can exist. Go ahead and build it. Okay, so you've got something like this. I'm going to use that one first, actually. So looking at this, what shape is that? It's triangle. It's trigonal. So we know it's trigonal something. The question is this all in one plane? Or does this form a pyramid? So let's get rid of this. And let's look at a side view of it. This is up here. These are down here. It forms 3 little triangular sides. It forms a very shallow pyramid. It is trigonal planar. I'm sorry. Ha! Testing. See? You're on your toes. That's good. No, I'm not testing. I just screwed up because I haven't finished my 3rd cup of coffee. Yeah, it's trigonal pyramidal. Sorry. It literally forms a little pyramid. How cute. Why does it do that? What's pushing those hydrogens down? That unshared pair. Pushes the hydrogens down and causes this to go from being all in one plane to looking like a little pyramid. Weird. Weird. Let's look at the ABE code for this. Let me get rid of that. Shrink this. So everything gets an A, right? Go ahead and try writing the ABE code for this, and we'll check in. Everything gets an A. How many things are attached? Physical things? 3. AB 3. Any unshared pairs on the central? 1. Usually if there's just 1, we don't write the 1 subscript. I didn't mark it wrong if you did, so if you wrote that, it's okay, but usually we don't. The presence of the E tells us that there's an unshared electron on the central atom, because that changes the geometry. So we want to know about it. Okay, let's do a nonconformer. Okay, we've got CH4. How many valence electrons should we end up with? Carbon has 4. Hydrogen has 1 times 4. So we have a total of 8 valence. If everyone was happy, I should really satisfaction electrons. How many electrons would everybody be satisfied with? Carbon wants 8. Hydrogen wants 2. So 16 octet, or 16 if everybody's fully satisfied. 16 if everybody's fully satisfied. They want 16. They have 8. They're going to have to share 8 electrons. Divided by 2 tells us we have 4 bonds. Well, that's an easy one to hook up. Sounds like we're jumping a car. Can you hook that up? Yes, I can. Are there any unshared electrons here? They have 8, they're sharing 8. No unshared. Because hydrogen can't have unshared pairs. It's got its hands full just holding on to one bond. Okay, so no unshared. Let's check and see if we've gotten everything on our list here. So there are no unshareds. Do we have 4 bonds? 1, 2, 3, 4. Check. Do we have 8 valence electrons? 2, 4, 6, 8. Check. Are there any unshareds? Nope. Is there any charge? Nope. Is there any place any of those bonds could be other than where they are? Nope. Okay, well that's easy. Now build this. Okay, so we've got an AB4. And this is one where I will say I think it can be kind of confusing. You all had geometry. There's our constructed methane. Lovely little cow fart. Yes, I think it's funny because, you know, I have the sense of humor of a 12-year-old boy. But, or girl. I think all 12-year-olds are entertained by farts. How many, if you've got that on your desk in front of you, take your hand and imagine a surface connecting those white dots. How many surfaces are there? 1, 2, 3, 4. Now those surfaces certainly look like they form a little pyramid, don't they? That's what I don't like about this. Booger. But there are 4 surfaces. What's the prefix that references 4? Tetra. Like Tetris. In the game Tetris, you can turn each piece 4 ways. That's why it's called Tetris. There are 4 surfaces. 1 surface, 1 plane. Hey, that's not too bad. Okay, you got your 4 minutes. We're going to come back and we're going to finish this idea. We're probably going to end up retesting tomorrow. All right. Does anything there clarify? I think AB4 was actually the one people had the easiest time with. People seem to know that one. Let's do a nonconformer. The dreaded sulfur hexafluoride, Sf6. It's this crazy looking thing. Whee! So let's try some math. What the heck? Why not? So, okay, how many valence electrons does this thing have? Well, sulfur comes in with 6. Fluorine comes in with 7 times 6, so we got 48. Is that correct? Okay. 6 times 8 is 48.
Yeah, 6 times 8 is
48. Ooh, boy. It's been a long morning already. Okay, so we got 48 valence. If everyone was satisfied, sulfur would have 8, fluorine would have 8. That would be 64. No, it wouldn't. 56, right? Wait, 8 times 7, 56. I can do calculus, I just can't do basic arithmetic. It's so sad. All right. So if we're trying to figure out if this is going to conform or not, because we don't know. Okay, we really do, but if we don't know and we're going into this, well, how many would they have to share then? 56 octet minus 48 valence. That would be 8 shared divided by 2 is 4 bonds. Is there any way to hook 6 things to a central atom with 4 bonds? Nope. Can't be done. So right there, you look at it and go, oops. Non-conforming. Does not conform. Can't be done according to the math. And yet, the compound exists. But it cannot be done. Okay. So, knowing that it doesn't conform, how on earth do we begin to draw this? Well, what's going to go in the middle? Least electronegative or carbon or the singleton? Sulfur. It's not only the singleton, we know fluorine is the most electronegative thing there is, so we know fluorine can't be central. Well, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Is everything hooked to the central atom? Yes. You know, do we have 4 bonds? No, we can't do this with 4 bonds. It's not possible. You can have more bonds than atoms. You can't have more atoms than bonds. How many unshared pairs are going to be there? We don't have math to fall back on. Because we already said this is not conforming to the math, so you can't do the math to prove how many unshared pairs there are. But what do you know about fluorine coming in? 1, 2, 3, 4, 5, 6, 7. So in each case, this one has hooked up with an electron from sulfur and it's sharing, it's formed a bond. Each fluorine is not going to give up those other ones that it came in with. Let me make that bigger. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Do we have any kind of double checks we can do on a nonconformer? Yes. One thing we can check. What is that? We can check to see if the total number of valence electrons that we're showing that we should be showing are present in our structure. It's the only thing we can do. So 6, 12, 18, 24, 30, 36, 38, 40, 42, 44, 46, 48. Do we have the correct number of valence electrons? Yeah. That's all we can do. It's the only check we can perform on a nonconformer. Now let's look at the ABE code for this. I'm going to shrink all the math. Central atom. Yeah, so it gets an A. Everything has an A. How many things are physically attached to the central atom? 6. A, B, 6. Are there any unshared pairs on the central atom? Nope, not a one. You're done. Did you build it already? Go ahead and build it real quick. Okay, you've got this constructed, and I actually had a couple of people come to me yesterday and say, okay, look, Moser, why is this octahedral when there are 6 things sticking off it? And I realized that something I need to change in my teaching for this in the future is we need to remember to look at the planes. Put your hand over each of the possible planes there. There's one surface. There's another, whoops, how'd that happen? There's another surface on the other side. There's another surface on the other side. There are 4 surfaces on that top. There are also 4 surfaces on the bottom. How many surfaces is that? 8. Oh, it's octahedral. Oh. I actually think, and shockingly, because I do that learning style survey at the beginning of the year and I actually look that stuff up and I go back to it, more of you are auditory than is usual. For kinesthetic and visual learners, for me, I can't see the shapes without these models. And I think for everybody, a lot of you are multimodal, so I think for a lot of you it probably does help. and I think I may, if I can figure it out, I'll let you do your retest with the models. You can actually have the models at your desk during the retest. And I think that would be helpful for you. Because I think visualizing these things is better than, it's better done with a model in front of you. Okay, let's go back to our checklist. Things that people had some issues with. Do you feel better about the ABE codes?
Yes.
Okay. What about shapes? Are there any other shapes you want to see? You want to see trigonal bipyramidal? Let's do a trigonal bipyramidal. Okay. Again, if you have this built, do you have it built? So I can't take a picture from the angle I want to. If we look at it on that plane, there's a triangle there. But then there's this little thing sticking up. So what it does is it forms a triangular face there. There are 3 triangular faces up. If we look at it like this. There are 3 triangular faces down. Guess what it forms? 2 triangular pyramids. Trigonal. Bi-pyramidal. Trigonal bi-pyramidal. Okay, here's what we're gonna do. Okay, so we have those as a proxy for, we have melting and boiling point as a proxy for the forces between either molecules or ions. One thing. Okay, it's typically we're talking about actually bonding within a single transition metal, but yeah, it's between transition metals. I guess if we have alloys of combinations of metals, we would still see metallic bonding in there. So it's between transition metals. That's the D block. That's the stuff that we look at and we think, hey, that's a metal. Iron and cobalt and nickel and tin and gold and silver. Real metals. Platinum, vanadium, titanium. Could go on all day. Chromium. Metals. One other thing you know about transition metal, about metallic bonding. Big thing in metallic bonding is that those transition metals have stuff in the upper Ds. Remember the metaphor we used. You move into your college dorm and you're the only person living on your floor. There are 10 empty rooms and none of them are locked. Oh my gosh, I can sleep in a different bed every night. I'm going to try out every single room. And so you move around. Woohoo! That's what happens with a lot of the transition metals because you've got those upper d orbitals that are acting like valence. Plus you've got maybe you've got unoccupied p's. And those electrons sleep in a different room every night. They move around. So you have mobile electrons. That's the feature. It's, the mobile electrons, the sea of free-moving electrons. That's why metals are such good conductors. The electrons move, they zip around, they fly, they go, go, go. Okay, what else do you know? What's attracting all those free electrons? Let's look at a chunk of iron, shall we? So how many... Iron's got 26 electrons, and on the top level, it's got 3s1, 3s2, I'm sorry, 4s1, 4s2, 3d, 1, 2, 3, 4, 5, 6. So it's got 6d electrons that are kind of free to roam around. Basically, once they start leaving that nucleus, what does it become? When an atom gives up some electrons, what does it become? A cation. It becomes a positive ion, yeah. Those little nuclei have lost some of their electrons because they can't keep a leash on the darn thing, so they just wander all over the place. So you've got all these little positive nuclei, and all these little mobile electrons. And it's obvious that, I didn't want to do that. They're gonna form attractions. You've got a sea of these electrons darting around all these little positive nuclei that are sort of like cations. So you've got forces of attraction in pretty much every direction. Can you melt metal in the lab on a burner? Probably not. Not with a candle. Not the way you can sugar or phenyl salicylate. Why do metallic compounds have higher melting points? Why do things that are metallically bonded have higher melting points? Reference this. The forces in between the individual chunks, the pieces, are a good proxy. We can measure them by proxy using melting point. You can't melt iron with a candle, fortunately. There are a lot of forces of attraction going in all directions in there. Okay, anything else? Okay. Tomorrow you're going to get your tests back. You're going to go back into test formation, and you're going to do corrections. If you want additional copies of anything, I can print some off. I'm out of molecular geometry labs. If you want to check out a model kit, so I think I'm just going to I'm going to have the model kits passed around. Like I'll have some people who start on the workout, some people can start on the multiple choice, and we'll just kind of have to share the model kits. I think I have 12, but that's half of you at a time can be using a model kit. So, okay, right now what I would like you to be doing is looking back over this stuff, looking for anything else that you feel like, crud. And is that it? I think that's it. Okay, good.